Hello everyone. In this lesson, we're going to be going over continuity. So looking at this slide, you see that a function f is continuous at a if the limit as x approaches a for the function f of x is equal to the function f of a. So this is the function at that point a. If a function is not continuous at a, we would say that f has a discontinuity at a or is discontinuous at a. A function is continuous from the left if the limit as x approaches a from the left on f of x is equal to f of a, and a function is continuous from the right if the limit as x approaches a from the right, f of x is equal to f of a. So pretty much what this means is that if we have some function, and let's say we have this function here, and we are approaching some value a from the left or from the right, if this point a, which would give us f of a, is equal to what the limit is as you approach that point, then we would say it's continuous. If it has a discontinuity, this might look something like this, where instead of including that point, we have a hole here, where it might be that this point just doesn't exist, or it could be something like this point exists at another place on our graph. So looking at this slides again, you might see that the first example, like I just drew, is what's called a removable discontinuity. That is to say that it's a function and it is continuous at most places except at a, because as we approach a, that point does not exist. So the limit as I approach a is not going to be equal to f of a. The second image we have here is an infinite discontinuity. This would be that as we approach zero from the left and the right, what's happening is it's going to go bigger and bigger towards infinity, and it's never going to be able to hit that point, meaning that there's, at that point a, in this case 0, you'll see that we actually do have a dot, so the point does exist, but neither of our limits will actually approach it. So we don't have continuity from the left or continuity from the right. The next graph is another example of a removable continuity, where again we have a hole, but this time we actually have a point somewhere on it. So that means that f of a does exist, whereas in the first one, f of a did not exist. And the last one is called a jump discontinuity. So there is a discontinuity, and it happens because as we're going from the left, we're approaching one value. As we're going from the right, we're approaching a different value, and it sort of makes a jump from one to the other. So it'd be something like this. You might see it as what we have here on this graph, where you have something like this, where it gets to this point, and then suddenly it makes the jump up to here. Or you might see it in this another case as sort of like a step function. Something like this, where you have a line, and then not included, and then maybe it jumps up, and then you have a line, and then it jumps up. And it does something like this, where you have multiple discontinuities, where each of these are a jump discontinuity. It jumps from one level to another, whereas if I'm taking the limit from the left, it will not be what the limit is from the right, just like with this one, right? When I approach the limit from left, I'm approaching this point. When I take the limit from the right, I'm approaching this point. They're not equal to each other. So while f of a does exist, and it's continuous from the right, because this is my f of a in this case, the point that's filled in. So my limit from the right is continuous, but my limit from the left is not. So let's say we have this graph here, and we want to label the discontinuities. So looking at this graph, as we go from the left, you will see that we have a discontinuity where that hole is. The limit from the left is equal to the limit from the right, meaning that they're approaching the same value, but that value does not exist. So for example, this might be x equals 2, which is a removable discontinuity, right? It's just missing, it's removed. As we approach from the right from there, you'll see that our limit from the left continues to go down and down and down until it gets to some point where then it does a jump discontinuity. So we have a jump discontinuity at x equals 5. And then continuing on to the right, we have another removable continuity where, again, it approaches the same value from the left and the right, so the limit exists, but the f of a at that point is a different point, meaning that it is not continuous at a. In this case, a equals 9. So based on this, this means that this graph is going to be continuous from negative infinity up to that first discontinuity of 2. And then it will be continuous starting at that discontinuity 2. Again, neither of those are inclusive, up to 5, not inclusive. And it'll start at 5 to 9, and then 9 up to infinity. So this might look a little bit like when we do a domain, but it's a little bit different, because if you actually look at the graph we have here, you'll see that we do actually have a point at x equals 9. So this is not the domain because I can, in fact, plug in x equals 9. I just have this removable discontinuity, but the point does exist. So now let's do some examples to see which of the following functions are discontinuous, or where they're discontinuous. So our first function, we have f of x is equal to x squared minus x minus 2 divided by x minus 2. So similarly to when we are trying to determine what our domain is, we first need to look at, is there anything that this function I cannot plug an x in for, right? So if I look at this, I cannot plug an x in at 2. Because if I do plug in 2 here, I'm going to get 2 minus 2 in the denominator, in which case this is going to give me 0 in the denominator, which we can't do. It's undefined. So that means f2 is undefined, which means that it's a discontinuity, right? We can't ever hit that point. So what's going to happen is as we take the limit from the left and or the right, it's going to probably approach some value, maybe going up to infinity, maybe going down to infinity, or maybe one side's going up to infinity, one side's going down to infinity, but it'll never actually be able to reach that point. So we'll never be able to have the limit as x approaches 2 on this function f of x be able to be equal to f of a, because at f2, it does not exist. The next function we have is gx is equal to 1 over x squared if x is not equal to 0, and it's equal to 1 if x is equal to 0. So we have this piecewise function here. So we have to consider what's happening whenever we have this function here. Well, on this first one, 1 over x squared, this is for whenever x is not equal to 0. So if we were to kind of graph this out, anywhere that's not equal to 0, this is the function that we're going to be using, 1 over x squared. And we could look at what happens as we plug in values, right? If we plug in 1, we get 1 over 1, so that's going to be 1. If I plug in 2, it's going to be 1/2. If I plug in 3, it's going to be 1/3. It's going to get smaller and smaller and smaller. And what happens as this value gets, the value x gets smaller and smaller? Well, it's going to cause the entire fraction to become bigger and bigger. Now, what about if we plugged in a negative value there? Well, what happens with a square when you plug in a negative? Well, it becomes positive. So it actually is going to have the same behavior. So what happens here is that we get something like this as we approach 0 from the left and from the right. Now, what do we actually get at 0? Well, according to our piecewise function, at 0, we have 1. So this means that we have a discontinuity at 1, because you'll see here that this goes off to infinity, this goes off to infinity. We do have the point, which means that the domain is that I can plug in any x value, but my limit as I approach 0 does not equal to what my function does at 0. So the limit as x approaches 0 on g of x is equal to this limit here, but it is not equal to g of 0. The next one we have is, what about if we have the function hx equals x squared minus x minus 2 divided by x minus 2 when x is not equal to 2, and we have that it's equal to 1 if x is equal to 2. So we're going to do the same sort of idea here, is that we're looking at what happens as we approach 2. So we're looking at the limit as h approaches 2 on, I'm sorry, not h, as x approaches 2 on our function hx. So when we're not equal to 2, meaning when we're approaching 2, we would be using this function here. So we're taking the limit as x approaches 2 for x squared minus x minus 2 divided by x minus 2. And in this case, we can't plug in 2, but we have an option for when the function is equal to 2. We said that it's going to be equal to 1. So again, we would need to look at what is the behavior of this function as we try to do that. So what I'm going to do is I'm actually going to split this into the limit as x approaches 2, and then this x squared minus x minus 2, I can set as x minus 2, x plus 1. Now, if we want to double check this, what we'll do is we'll just see if we can distribute this back together, see if we get the same thing. So we get x times x, or first outer inner last, so we get x squared. We get our outer, which is plus x, our inner, minus 2x, and then our last, minus 2. Well, x minus 2x is going to give us negative x, negative 2, so yeah, that looks good. So now what I'm going to do is I'm just going to cancel out these x minus 2's, and I'm going to have the limit as x approaches 2, x plus 1, which means that if I plug this in, I'm going to get a limit of 3. So my limit as x approaches 2 is going to be equal to 3. But my function, h of 3, is equal to 1 according to this piecewise function, which is not equal. So therefore, we have a discontinuity at 3, because 3 does not equal 1. The last one we have here, this is, so we have capital F of x equals the floor function of x, which means basically whatever values we plug in for x, we are going to be taking the greatest integer. So for negative 1, we would have a value of negative 1. And then it'll stay negative 1 until you get to the next integer, which is 0. And then suddenly it makes a jump up to 0. And then from 0 to 1, not including 1, it will be at 0. Once it gets to that next integer, 1, it's going to jump up to 1. And then we'll have a line at 1 up until it gets to 2. Then it jumps up to 2. Then it stays that line until it gets to 3. So this is actually a step function. And if you look at it, we actually have a discontinuity at every single integer. Because if you look at negative 1, we start at negative 1. And then once we get to 0, we jump up to 0. Once we get to 1, we jump up to 1. Once we get up to 2, we jump up to 2. So in this case, this one actually has a whole bunch of discontinuities, which means that if we were to look at this, this is actually continuous only from the right. Because if we're coming from the right, the function at that integer is equal, right? So if we look at this graph, let's say we look at f of 1. F of 1 is going to be equal to 1. Well, if I take the limit from the right of 1, so the limit as x approaches 1 from the right, it will be equal to 1. So it is continuous from the right. But if we look from the left, as we approach that point, again, say 1, so we have the limit as x approaches 1 from the left, the limit is approaching 0, but the function is equal to 1. So in this case, it is continuous from the right, but not continuous from the left. For our next example, we want to show that the function f of x is equal to 1 minus the square root of 1 minus x squared is continuous on the interval negative 1 to 1. So that means on the interval from negative 1 to 1, inclusive, meaning it includes negative 1 and includes positive 1, we want to show that this is continuous, which means that we want to say that if we have f of negative 1, what is this equal to? So if I plug in negative 1, I'm going to get negative 1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. So this is going to be equal to 1. If I plug in positive 1, I'm going to again get 1 minus 1 squared. 1 squared is 1. 1 minus 1, square root of 0 is going to be 1. So we have right now that f of negative 1 and f of 1 are both going to equal to 1. So in this case, if let's say that we have some a that is between these two values. So we're going to have a that is between negative 1 and 1, right? Our two x values, right? So we're just saying that a exists somewhere in this interval. So what we're going to do is we're going to take our limit as x approaches a, and we're going to plug in our function. So we're going to have 1 minus the square root of 1 minus x squared. And then, of course, using our limit laws, this is going to be the same thing as the limit of 1 minus the limit of this. So it's going to be limit as x approaches the point a, 1, minus the limit as x approaches a, square root of 1 minus x squared. Well, this first term, we have the limit of a constant. That's just going to be the constant. So limit of 1 is just going to be equal to 1. Now we have minus, so we have 1 minus the limit as x approaches a, square root of 1 minus x squared. Now, using our limit laws, we can actually rewrite this as, we have 1 minus, I can take the limit of the function that's inside all to the square root, right? If I have the limit of a square root, it's the same thing as taking the square root of the limit. So this is going to then be the square root of the limit as x approaches a, 1 minus x squared. So right now we have this, and we can evaluate it just like we did before. I can take the limit of the first thing, it's constant 1, so it's going to be 1, and I take the limit minus the limit of this. So we're going to have 1 minus the square root of 1 minus the limit as x approaches a, x squared. And last thing we're going to do is we are going to plug our a value in, which is going to be 1 minus the square root of 1 minus a squared. And then I can actually see if I can solve this. Is this equal to f of a? Well, it is equal to f of a because if you remember, based on our original setup that we had 1 minus the square root of 1 minus a squared, which is the same exact thing that we would have in our original function. So that means that f of x is in fact continuous on -1 to +1 inclusive, right? So all we did basically is we showed that by solving the limit and plugging a in for x, we still get a function that f of a, which is equivalent to what we did with when we had it in terms of x for our function f of x. So pretty much what we've shown is that if I take the limit of this, it will still be equal to the same thing. Therefore, it does, in fact, it is continuous in that interval. So next what we want to talk about is if we have two functions, f and g, that are continuous at a, and we have some constant c, then this means that the following are continuous at that point a. If you take the function f and add it to the function g, it will still be continuous at a. If you take the function f and you subtract the function g, it will be continuous at a. If you take the function f and multiply it by the function g, it will be continuous at a. And if we take the function f and divide it by the function g, this will also be continuous at a, as long as g of a does in fact exist. Because again, we have a fraction, we can't have a 0 in the denominator. If g is continuous at some point b, and the limit as x approaches a for g of x is equal to b, then this means that the limit as x approaches a for f of g of x is going to be equal to the function f of b. So what does this mean? It just means that if we have that our limit as x approaches a on g of x is equal to b, we could then substitute that in for g of x as x approaches a, which means that we'll have the function f of what that is equal to now is b, so f of b. Or, that is to say, if we take the limit as x approaches a, f of g of x, this is going to be equal to f of the limit as x approaches a, g of x. So we can substitute in that limit, which we said was equal to b. And if g is continuous at a, and if f is continuous at ga, then f of g of x will equal to f of g of x, and it's going to be a continuous function, right? So in this case, we're just writing it in the two forms and saying that, in fact, it is continuous here if you take a composite of two or more functions. As long as they are each continuous individually, they will all be continuous together. Some other rules that are actually really useful is any polynomial that you have is continuous everywhere. So polynomials are continuous everywhere. That is to say that it is continuous for all real numbers, meaning it has a continuity from -infinity up to infinity. Any rational number, root function, or trig function is continuous at every number in their domains. That means, for example, if I have something like f of x is equal to the square root of x, this means that if I know my domain, which in this case the domain would be from 0 inclusive up to infinity, this means that it is continuous from 0 to infinity. If I have something like 1 over x, let's say we have g of x is equal to 1 over x, then in this case, what is my domain? My domain is I can plug in anything that's not 0. So the domain for this one would be from -infinity up to 0, union 0 up to infinity, meaning that this function would be continuous everywhere except 0. For our next example, we're going to start with the fact that f and g are continuous. I'm just going to put cont. If f of -1 is equal to 2, and the limit as x approaches -1, 3 f of x minus g of x is equal to 0, let's find g of x. So how would we go about doing this? Well, we're going to start with this limit here. We have our limit as x approaches -1 for 3 f of x minus g of x. And we're going to then use our limit rules to take the fact that we can take the limit of this minus this as the limit of this minus the limit of this. So this is going to be equal to the limit as x approaches -1, 3f of x, minus the limit as x approaches -1, g of x. And now that we have it in this form, we have the limit of a constant times our function. I can pull that constant out, so I'll have 3 times the limit of x approaches -1, f of x, minus limit as x approaches -1, g of x. So let me write that down real quick. We have limit as x approaches -1, sorry, we got the 3 on the outside, f of x, minus the limit as x approaches -1, g of x. Now, based on the facts that we were given, f of -1 is equal to 2. And if we plug in a limit as x approaches -1, what we can do is we can plug that -1 in. And as long as it exists, we'll be able to get the limit. So this is going to end up being 3 times, plug in -1, which is going to give us 2. And if we were to plug in -1 into this g of x, we'll just replace that. So now we have minus g of -1. So now we have 3 times 2 minus g -1. Well, we did say that this entire limit was going to be equal to 0. So we're going to set this equal to 0. So we have 3 times 2, which is equal to 6. So 6 minus g at -1 is equal to 0. So with this now, I want to isolate my g of -1. So because this is negative, what I'm actually going to do is I'm going to add g of -1 to both sides, which is going to give me 6 is equal to the function g at -1. So therefore, we now know what is g of x as the limit as g of x as we approach -1, right? Because I actually wrote this wrong. This should have been g of -1. Sorry about that. In this next example, we want to consider that we have the function f of x is equal to x squared minus x divided by x squared minus 1 if x is not equal to 1, because if we plugged in 1, we would get 0 in the denominator, and 1 if x is equal to 1. So we have this piecewise function, and what we want to do is we want to find the limit as x approaches 1 for f of x, and then of course we also want to figure out what is our function at 1. So we're going to start with our limit. So our limit as x approaches 1, well, remember, our limit as we approach 1 is not equal to 1. It's everything but 1 as we get closer and closer and closer, infinitesimally close, but never actually touching it. So we're going to be using this function up here. So we're taking the limit of x squared minus x divided by x squared minus 1. Now, if I were to really quickly just try to plug in 1, we already talked about the fact I'm not going to be able to do this because I'm going to get 1 in the denominator, so 1 squared is 1, 1 minus 1 is going to be 0. So I need to do something to try to simplify this to make it where I can actually take that limit. So what I'm actually going to do is I'm going to take the limit as x approaches 1, and I am going to pull one of these x's out from the top. So we have x squared minus x. Both have x in it, so I'm going to pull one of these x's out. I'm going to get x times x minus 1. And for the bottom, I have that this is a square function, x squared minus 1, which means that I can actually rewrite this as x plus 1, x minus 1. And if you just want to double check, as we always do, FOIL it out. X times x is going to give me x squared minus x plus x minus 1. The minus x and plus x will cancel. I'll be left with x squared minus 1. Now, based on this, the top and the bottom both have an x minus 1 that I can cancel. So now I am left with the limit as x approaches 1, x over x plus 1. Now, if I were to evaluate this limit, I would use my limit laws. I would take the limit of x over the limit of x plus 1, and then I would split the limit of x plus the limit of 1. 1 is a constant, so it would just be 1. But I'm just going to plug it in, and I'm going to get 1 over 1 plus 1, which is equal to 1/2. So next thing we're going to do is we're going to look at, this is our limit of f of x, right? We talked about our limit as x approaches 1, f of x, we said is equal to 1/2. Now what we want to do is we want to figure out what is our function at 1. And this is going to be equal to 1, because we said if x is 1, f of x is equal to 1. So in this case, it is equal to 1. And we're going to look at, is it continuous? Well, if it's continuous, this means that the limit as x approaches 1 f of x would have to be equal to the function at 1. And these two are, in fact, not equal, meaning it's discontinuous at x equals 1. So when a is equal to 1, this is discontinuous. For the next example, I'm going to find the limit as x approaches 1 for 8 plus the square root of x divided by the square root of 8 plus x. So in this case, if I were to try to plug in 1, what's going to happen? Well, I'm going to get 8 plus the square root of 1 divided by the square root of 8 plus 1. So the square root of 1 is just going to be equal to 1. So the top's going to be 8 plus 1. 8 plus 1 is 9, so I'm going to have the square root of 9, which is going to give me 9 over 3, which is equal to 3. So in this case, I actually got a limit just by plugging it in, which means that if this is my function, 8 plus square root of x over square root of 8 plus x, and I plug in 3, so I would get f of 3, I'm going to get 3. When I took the limit as x equals 1, I also got 3. So therefore, in this case, this would be a continuous function, because the only thing that's going to cause an issue is if, in this case, I tried to plug in a negative 8 or something that's going to make it negative, which means anything less than negative 8, right? So if x is less than or equal to negative 8, this would cause it to not exist. So the domain of this function is negative 8 up to infinity, meaning that this is actually continuous anywhere on this domain, because this would be a rational function or irrational function or any of those other ones we talked about, which means that it is in fact continuous at x equals 1. What about if we wanted to find the limit as x approaches pi on the function 2 sine x plus sine of x? So in this case, we're going to take the limit of 2 sine, and within the sine is x plus sine x. So whenever you have something like this, and this is why the first step I always say is, first let's see if we can plug it in. If we plug it in and we get a value, then we have the limit. We don't have to do any tricks. We don't have to do any ways of canceling anything out. So what we're going to do is we're just going to try plugging this in. So if I plug this in, which means I'm going to evaluate this limit, I'm going to have that this is equal to 2 sine of pi plus sine pi. Now, what is the answer of sine equals pi? Well, let's look at what a sine wave does. So a sine wave starts at 0, goes up, goes down, comes back up. And of course, it's at 0 at 0. It's at 1 at pi over 2. It's back to 0 at pi. It's negative 1 at 3 pi over 2. And it's back to 0 at 2 pi. And then it's going to repeat this over and over again. So at sine of pi, we have that the answer is it's equal to 0. So this is going to go to 0. So now we have 2 sine of pi plus 0. Well, pi plus 0 is just pi. So that means we're basically looking at what is 2 sine of pi. Well, we just said sine of pi is equal to 0. So this is going to end up being 2 times 0, which means that the answer is 0. So looking at this slide, we're going to be looking at, for these different functions, where are these functions continuous? So the first one we have f of x equals x to the 100th power minus 2x to the 37th power plus 75. Now in this case, because this is a polynomial function, remember that first rule we had, polynomial functions are continuous on the real number line, which means all possible values. So this one will be continuous from negative infinity to infinity. The second function, g of x equals x squared plus 2x plus 17 divided by x squared minus 1. Now in this case, because this one is a fraction, a rational function, whatever you want to consider it, it's wherever its domain is, that is where it's going to be continuous. So we want to look for where we cannot plug in an x value. What is its domain? So looking at the denominator, so the top is a polynomial, meaning the top doesn't have any restrictions. It can be any value. But if we look at the bottom, I have x squared minus 1. So if I were to plug in a positive 1, I would get 1 squared is 1. 1 minus 1 is 0. I'd get a 0 in the denominator. If I plug in a negative 1, negative 1 squared is positive 1. Positive 1 minus 1 gives me a 0 in the denominator, meaning that x cannot be negative 1 or 1. This means that this function will be continuous from negative infinity up to 1, not inclusive, union, -1 to 1, not inclusive, union, and then 1 to infinity. So basically it is continuous anywhere on the number line except at -1 and +1. For the third function, we have hx is equal to the square root of x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. So in this case, again, we are looking at the fact of where can we not plug in an x, meaning it's not part of our domain, that would cause this to fail. So I'm going to start by looking at the last part of this function, x plus 1 over x squared plus 1. Now, I can plug any value in for x here, because even though there's something in the denominator with an x, what's going to happen is if I plug in a positive value, I'm going to get a positive outcome. So positive value plus a 1 is going to be equal to something positive. If I plug in a negative value, that square is going to make it positive, giving me the same thing. So the last term has no restrictions on it. Then we're going to look at the middle term, x plus 1 divided by x minus 1. The numerator has no restrictions on it, but x minus 1 does. It says that we cannot plug in a 1 into this part, because if I plug in 1, the denominator will be 1 minus 1 or 0. So x equals 1 is something it's not in our domain. Now we look at the first term. We have the square root of x. Well, we talked about before, the square root of x can be any value from 0 inclusive up to infinity, meaning that this function, this part of the function, is anything greater than or equal to 0, which means that our domain would be 0 inclusive, so square bracket 0, up to 1, parentheses, union, parentheses, up to 1, up to infinity. So in this case, this is where it would be continuous. It would be continuous anywhere from 0 to 1, not including 1, and anywhere from 1 to infinity. For this next example, we're going to have a constant c that we want to determine where this would cause our function f to be continuous on our number line negative infinity to infinity. So if we have the function f of x is equal to the constant c x squared plus 2x if x is less than 5, and we have that this function is equal to x cubed minus cx if x is greater than or equal to 5. So we have this piecewise function. What we want to do is we want to see what value of c would cause this to be continuous. Now remember, for this to be continuous, it means that as I take the limit from the left, it has to be equal to the limit from the right. So this, when x is less than 5, means that as I approach 5 from the left, this is my function I'm going to use. Because this one is x greater than or equal to 5, as I approach 5 from the right, this is the function I'm going to use. So what I'm going to do is I'm going to set the two functions equal to each other. So I want the limit as x approaches 5 from the left on my function f of x, and I want this to be true where it is equal to the limit as x approaches 5 from the right on my function f of x. So now what I'm going to do is I'm going to plug both of these in. Well, I said that as I'm approaching from the left, it's going to be this. So this is going to be the limit as x approaches 5 from the left is going to be cx squared plus 2x, and then this is going to be equal to my limit as I approach from the right, so limit as x approaches 5 from the right, and I'm going to plug this function in, x cubed minus cx. And so now what I'm going to do is I'm going to evaluate what both of these would be if I were to plug in 5. So this first one, right, because basically what's happening is, if we want to think of it piecewise, is that I'm going to take the limit of this first term plus the limit of the second term. That c is a constant, I can pull that out. So actually, you know what, I'll do that just to show you guys the steps. So this would then be the limit as x approaches 5 from the left, cx squared, plus the limit as x approaches 5 from the left, 2x. I'm just going to focus on the left right now. This is a constant c, so I can pull this out. This 2 is constant, so I can pull this out. So I'm going to be left with the limit as x approaches 5 from the left. It's going to be c times that, x squared, plus 2 limit as x approaches 5 from the left, x. Now, if we look at the right side, it's going to be the same idea. I can take the limit of the first term minus the limit of the second term. So this is going to be the limit as x approaches 5 from the right, x cubed, minus the limit as x approaches 5 from the right, cx. Now, because I have this constant in front, I can pull this out. This is going to be equal to the limit as x approaches 5 from the right, x cubed minus c, limit as x approaches 5 from the right, x. And now what I'm going to do is I'm just going to plug in 5 for anywhere that I have x. So in this case, this is going to be c times 5 squared plus 2 times 5 equals 5 cubed minus c times 5. And I just need to solve for my c now. So this is going to be 25c. I'm going to pull this over here. This is going to be 25c plus 10 is equal to 125 minus 5c. And now I just need to solve for c. So I have 125. If I were to subtract 10, so I'm going to subtract 10 from both sides, I'm going to add c to both sides. I'm going to be left with 30c is equal to 115. And then I'm just going to divide both sides by 30. And I will be left with c is equal to 23 over 6. And now this would be the c that if I were to plug this in to this original function, right, this piecewise function, this would make it continuous, which means that as I take my limit from the left, it is going to be equal to my limit from the right, and they're going to meet at the same point. So we're going to end off this lesson by looking at the intermediate value theorem. So suppose you have some function f is continuous on a closed interval a to b. Let n be any number between f of a and f of b, right? So we have our boundary conditions a and we have our boundary condition b. And we have n is some number between the function at a and the function at b, where f of a is not equal to f of b. Then that means that there exists some number c in our interval a to b such that the function at c will be equal to that n. So looking at this graph, what this kind of means is that if I have my boundaries a and b, and I have some points on a and b at the boundaries which are not equal to each other, that means that somewhere in this interval there will be some c where it is the function at c will be equal to that point n, meaning that it has to hit every intermediate value. So if I have some a, right, so let's say we have this. If I have some a here and I have some b here, and let's say that I have a dot here and a dot here, at some point between these two, at least one point, but it could be more, I'm going to have to cross whatever value n is between these two. So if n is here, let's say, this means that I could have a straight line where I will hit n right here, or it could be something like this where I go up, I go down, and I come back up. Well, guess what? I've hit n here and here and here. So what this is saying is just that if I have this closed interval a to b, that to get from f of a to f of b, at least somewhere in this interval, I will have to cross this point n, which is between f of a and f of b, right? So f of a is here, f of b is here, and if n is between f of a and f of b, as I go from a to b, I will have to have crossed n at least one time, right? So pretty much what it's saying, it seems pretty intuitive. To get from a to b, I would have to cross every point between here, right? I'd have to go from every point from f of a to f of b, meaning somewhere in here, this n will get crossed at least one time. Now, in some cases, as I said, you may be able to find more than one number. So if you kind of look at this slide here, I have a graph kind of like what I drew here, where I have a sort of sine wave looking kind of function where it goes up, it comes back down, it goes back up between f of a and f of b, which means that in this case, it would actually hit at some c1, some c2, and some c3. It'd have 3 points where it actually crossed that point n. That's between f of a and f of b. Now, note, this intermediate value theorem does not tell you how many times you will cross, just that you will have to have had crossed at least once. So it's sort of like a proof of existence. There exists somewhere in this interval where it has to be true that this outcome exists. So in this problem, we want to use the intermediate value theorem to show there's a solution for a given equation on an interval 1 to 2. So we have x to the 4th power plus x minus 4 is equal to 0. So our function f of x is equal to x to the 4th plus x minus 4. Now this is continuous because this is a polynomial function. As we said, polynomial function is continuous on the entire real number line. So what we're going to do is we're going to first figure out what our boundaries are. So we have f of 1, and we're going to plug in 1 wherever we have an x. So 1 to the 4th power is 1 plus 1 minus 4. So we're going to get -2. Then we're going to plug in our our right side boundary, which is going to be 2. So we're going to plug in 2. 2 to the 4th power plus 2 minus 4 is going to give us 14, which means f of a is equal to -2. F of b is equal to 14. That means that to check whether this point, there in fact is some solution to this problem, x to the 4th power plus x minus 4 equals 0, we would need to show that, in fact, the 0 exists somewhere between -2 and +14. So, and it does, right? If I'm going from -2 up to 14, I will have to cross every value on the real number line between -2 and 14, meaning that, and 0 is in that interval, which means that there is at least one solution where this is true. X to the 4th plus x minus 4 equals to 0. Similarly, if we want to show that the equation x to the 4th plus x minus 3 equals 0 has a solution on this interval 1 to 2, we do the same idea, right? We have our f of x, which is equal to x to the 4th plus x minus 3, which again, polynomial, which means it's continuous in that interval from 1 to 2. I'll plug in my boundary condition, so I plug in 1, I get 1 plus 1 minus 3, which is going to give me -1. That's going to be less than 0. For our right side boundary, we're going to plug in 2, which we're going to get f of 2 is equal to 2 to the 4th power plus 2 minus 3, which is going to be equal to 15. And this is greater than 0, meaning that basically to go from a negative value, which is less than 0, up to a value greater than 0, means we would have had to have crossed 0 at some point to get there. So this, by our intermediate value theorem, then we can say that there exists some number c on the interval 1 to 2 where f of x does in fact equal 0. Now, as a reminder, this does not tell us how many solutions there are. There could be more than one. All this states is that at least one solution to x to the 4th power plus x minus 3 equals 0 exists on the real number line in this interval between 1 and 2. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.